Welcome to Counting Cars. And I just wanted to start with a quick disclaimer. This is not the official congestion pricing data. This is kind of a passion project Tim and I have worked on since around like third week of December. If you want the official congestion pricing data from the MTA, that is in room 301.
Yes, excellent disclaimer. Another disclaimer, this is not journalistic integrity or rigor at its finest. If you want like the real journalism, probably go to the other talk as well.
301.
We are two hackers just looking through cameras, trying to count cars as best as we can.
So yeah, just that quick disclaimer, because I realized they scheduled both congestion pricing talks at the same time on the same floor. So want to make sure folks are not confused. So this is just a project we've kind of just, as techies, worked on for about a few weeks, and the official MTA head of data science is in 301. So quick disclaimer there. So yeah, this is about counting cars, visual cognition and traffic in NYC. And on this cover image, you kind of get a hint of what we're looking at, which is trying to count cars using a computer vision algorithm. So the MTA, as I just said, has great data. It's publicly available. They actually did a great job making the official congestion pricing data pretty much open. And this is what the open data law was about, was to make this possible. So that's the official publicly available MTA congestion pricing data. The MTA, that data comes from around 1,400 cameras at 10 detection points. So an average of 140 cameras at each cluster point. And that's where they read the license plates of cars coming into the congestion relief zone.
And this, everyone here is familiar, we hope,
yeah,
with
nothing
the
new.
Congestion relief zone. It's right from 60th down. There's a ring of cameras around here that we're going to try to look through and count things on. Maybe we could quickly just mention who we are. And
sure. Oh yeah, I missed that part, didn't I? Okay, so yeah, I'm the organizer of Transit Techies. I see a lot of Transit Techies regulars here. And so we're a monthly meetup, and we meet at NYU to just really talk shop about transportation and technology. I've been running the group since like 2022, but it's been around since 2018. And yeah, so that's who I am. And I work as a machine learning engineer by day. So that's
nice.
Tim.
Yeah, so Isaac's the engineer, and I'm sort of the designer anthropologist. I've been playing with interactive media and visual cognition stuff in a lot of different ways for quite a while. I'm currently teaching communications and innovation management in London. And this passion project came about because Isaac and I were chatting about other stuff with like, what can a machine learn, or are we anthropomorphizing these intelligences? And just, we ended up, geeking out a little bit, saying like, oh, what if we just, and it turns out Isaac could, I couldn't, I would just like along for the ride, actually, ingest this visual data and try to make some sense of it. So that's who we are, and sort of how we got started on it.
And that's the background of the project. And we actually started before congestion pricing. We have about like 5 days of data from December 26th. And the goal there was to try and understand the beginning and after, because I assume we're never going to go backwards. But unfortunately, getting data during the holidays isn't a real apples-to-apples comparison. So we're only going to stay talking about like the actual from January 5th congestion pricing data. But yeah.
Okay, so we've got this zone. We've got, the MTA has, 1,400 cameras. Let's
and
continue on.
Clustered across 10 detection points. We use cameras at these 225 points. And by we mean DOT, which is the Department of Transportation. They have cameras scattered throughout the city, a little less than 1,000, I think 800 something. And those camera feeds are publicly available. And I just took a screenshot every minute of every camera and counted the cars.
So we're not looking through the MTA cameras, to be clear. We're looking through the DOT cameras.
So these cameras are not, the feeds for these cameras are not publicly available.
And this is a question we have. So one question originally, I mean, we can go on, let's show it a little bit more, and then we can get into the nuts and bolts of how. But this is sort of, a model that I try to use is thinking about data, transforming it into information, making that information into knowledge, and then hopefully reflecting on that knowledge to use some wisdom before actually taking action. And so there's a lot of stuff being done with all of this data, the MTA data, the DOT data, but we don't necessarily, even though it's amazing this public data is available, we don't really have all access. And I think I personally would like more access. As great as the MTA data is, we're actually not using their cameras. And so what we had hoped to do in the beginning was compare our machine with theirs, right? See if like our count matched their count. So let's move on to the next slide just to set the scene a little bit and also give away like, this is it. This is what we counted. We counted cars, and we have to question what is a car, what is an object. We're going to go into some of those. How do we detect yellow and get rid of it? But long story short, we counted less than they did. Probably their data is probably more accurate. Well, probably.
Well, yeah,
But it's interesting.
Can I mention a quick reason why?
Yeah,
so
of course.
The MTA cameras count license plates. So that is the ground truth of what's being counted. We're counting, as you'll see, the physical car. So we have an object recognition algorithm that counts, hey, this is a car, this is a truck. That we don't have understanding of what is a taxi based on a physical description besides the color. And that pretty much excludes Ubers because Ubers are typically black. From my perspective, from the DOT cameras, is it black car an Uber or is it a private car?
And conversely, their data, if you put a license plate of any kind of, taxi limousine on any vehicle, we don't know this 100%, but if they're just looking at the license plates and not taking into account the color and shape and velocity and other criteria about the vehicle, they're just counting a taxi. So they also probably have some margin of error, of course, but we're sort of looking at things slightly differently and sometimes calling things different. Like that was interesting to me going through like what we call trucks and what they call trucks. And they also, because they're counting license plate, can like exclude some people who aren't really going into the zone.
Yeah. So for example, if you're driving down FDR, they don't count that in the congestion pricing data because the MTA has excluded roadway entries where you're not actually going into the relief zone, you're just passing through. So they subtract those values. If our cameras catch those counts, we count those. And a few other nuances we'll get into.
We also are comparing sometimes apples and different kinds of apples, hopefully. But, we've got like a jump start on them. They're official.
Sure, yeah. So we started this pilot project just from a few conversations right after Christmas. I just like coded it up to try and get it to just some data. So our data starts from December 26, 2024. Obviously, congestion pricing started January 5th, 2025. So long story short, do we trust our numbers? No.
But it was fun to count.
It was fun to see. And I think the story, really the main character in our talk is the DOT cameras. Their feeds publicly available, rich with information. I think you could get a lot from them. They may not be the best for counting cars for congestion pricing, but I think the fact that the DOT cameras are so rich with data and it's just like openly available for the taking is pretty awesome. So to add it up, this is our estimate of how much money the cars made for the city, about 109 million. Obviously, with the real count, it's much higher than that.
And we're trying, by the way, here just to encourage all of us to like go. We'll show you how we did it. It's pretty easy. It's not super user friendly in some ways, but it's not that hard to access this visual data and try to make sense of it ourselves.
Yeah.
And then we can do some basic math like this. We had hoped also to look at like how much pollution is coming in and is it moving down. But a big question that a lot of citizens have as you sort of do some basic research, so as kind of ethnographer, and I've not done any formal research for this one at all, but just starting to take a temperature of New Yorkers in different boroughs who use and don't use transport. It's a big, complicated question, but a lot of people wonder, like, well, where's the money going? Like, if it's the state, not the city or not my borough. And so hopefully you can use some of the basic ways that we used to do this yourselves and count something even more specific, maybe even a one specific camera and just say, look, I'm looking at this bridge, like the Ed Koch bridge you'll see, and we can share those numbers, validate and participate. That's the idea. So yeah, I was just like, okay, $110 million, like 109. Okay, 109. Let's not quibble.
Yeah.
$110 million. Where's it going?
So yeah,
here comes it.
What is visual data? So how we count cars from images.
Can we go back just to one? This is a bit philosophical maybe, but this is the intersection between Isaac and mine. Like we're looking at other ways of using machine learning to look at things and make art and stuff. But my background as a designer and as someone thinking about like, how do we interpret signs and what is actually going on when, you are in a subway car, visual data, like there's a big question. And what what I discovered through this last few months is like, oh, wow, it's really hard. Like our machines are just not really there yet. So there'll be nothing better than paying a human being, I think, to sit and just watch and take count. We're so much faster, better, stronger than the machines. But okay, let's go on. That's a bit of a philosophical tangent, and now comes the
actual data. So we're gathering data from this website. This is where you could poke around and play with the DOT cameras, pretty much openly available for everyone. This existed before congestion pricing. I don't know since when this has been up, but this is old news. And so
has anyone used this before? Have you guys seen this? Some of you have used it a little bit. Yeah.
Awesome. Yeah. So these are the DOT camera feeds.
It's been at least since November, right? Am I not mistaken? Like I feel like there's been a couple months in last year where I was poking around looking.
Yes, I remember poking around with this in like 2021.
So these cameras were already online in 2021.
Yeah, at least probably.
And when did the MTA cameras go up? Do we know?
I think they got put up more recently, less than a year before it actually activated. I'm not sure on that though, but but these cameras are really old, and you can kind of tell by the resolution. These are not no license plate resolution here. That's part of the reason why we had to count the physical cars. The resolution on the DOT cameras are pretty bad. So how do we get the locations? I think it's probably better if I do a demo here.
So we're just going to show you exactly how we did it. There's some slides afterwards that will repeat the instructions. And
so here's that website for the DOT cameras. I'll pick a random camera in the congestion zone. Now I'm just looking at this random feed at 11th Avenue and West 40th. And how we got the metadata for the cameras is it's a little convoluted, and honestly, without a tech background, it'd be hard to think of this. But if you open the camera, right click, open it in a new tab, this URL here, can you see it? Oh, I can't. Hold on.
So basically just, right clicking, looking at source code. We've got the image in its own window.
Sure.
We take the URL of the.
So we see the URL there. And what I'm going to do is I'm going to backtrack all the way up until the URL is just API/cameras. Press enter, and I get all the metadata for every single DOT camera.
That's it.
Not hard, but super hacky. Usually large enterprises don't have their API database exposed like this, but government's not the most tech savvy, so
well, it's open data, right? It's open.
It's open data. If I zoom in here, you can see pretty much everything about every camera. So you see the latitude, longitude, the area that it's in, the name of the camera, and the camera ID, which is most important for analysis.
It's interesting, by the way. I just think like information architecture wise that we've got obviously like an ID and then also camera names, which will come in a little bit later, like distinguishing, being able to communicate via camera name or specific camera ID. But yeah, that was a fun little hack, right? Just go to a URL like, oh, it's all there. And so then Isaac basically brought that data into his little app, and he's got a computer running in his basement, literally just with those URLs open, snapping pictures of the screen. And, just the low res, that image part in the center.
Yeah, so that is how we got the data. And this is just the instructions that I just went through. So you go through the DOT link for all the cameras, click on a random camera, open it in a new tab, and then just delete the ID and you up until cameras, and you'll be left with the DOT camera database exposed in your browser. So yeah, and I made a note there. Usually an enterprise would not have their underlying database exposed like this, but technically it's open data, intentional or not.
And I'm super, I'm not a dev or a programmer. I haven't done stuff like that for 15 years, but it is super fun. And it's not, you can, with Supabase these days, you can get other connections if you can get to the data source. Yeah. Sometimes just a phone call and asking and someone to open a port for you works. So there's a lot of data out there to be ingested.
And so here's the technical details of the process. So we use the YOLO V5 algorithm. YOLO stands for you only look once. And it's on the 5th generation of that algorithm. So it's a lightweight industry standard image recognition algorithm that's been trained on cars, trucks, and I think 80 different classes of objects. So anyone who's working machine learning is aware of this kind of like standard cookie cutter visual recognition algorithm. And so I just used it. We ignore buses and motorcycles, unlike the MTA database, A, again, because we don't have access to license plate resolution. But B, YOLO doesn't recognize motorcycles. It does recognize buses, but when I actually deployed it to try and find buses, it was pretty bad. It was pretty much a coin toss on whether or not a bus would be classified as a truck, a bus, or a car. So I just took buses out entirely.
And I just completely blindly trusted Isaac to choose the algorithm. Like there are others maybe that we could have looked at, but we just wanted to tinker as quickly as possible. And so as I understand it, this particular model was not trained. It was trained on a lot of stuff, but not at all on yellow taxis.
Right.
So we had to make up our own way of saying like, this is what yellow is for our count.
Sure, yeah.
And can I tell this embarrassing story real quick?
Sure, go ahead.
That was sort of funny. Like in the very beginning, we were doing some other stuff, again, on a machine physically with Isaac. And we accidentally stopped the counting. We stopped running for a couple of weeks in December. And so, yeah, human error is like always, you know, an important part of the process. But I think let's look at some of these, like recognizing what is a car, what is a truck, why is it?
So yeah, where our eyes, there are 884 DOT cameras. We use these 225 in the congestion zone. I had to handpick some of these because in the metadata, there's a field for cameras in Manhattan. And then I originally did that. I was just like, give me all the cameras in Manhattan. I'm okay filtering everything above 60th Street. But an issue that came up was there were some cameras pretty much on the Brooklyn and Manhattan bridges and into downtown Brooklyn that were labeled as Manhattan in the metadata, but I'm physically looking at it, it's clearly in Brooklyn.
If you go a couple of slides up, we have a slide.
Okay, cool. So yeah, we use 225 out of the 884 DOT cameras. Here's an example of what our data looks like. The only difference, one of the differences, we have camera IDs.
You're going to see TT and CP. CP is what we call congestion pricing. That's basically the MTA data. And TT is transit techies. That's our little, algorithm here. It's only 123 lines or so of code. And yeah, there's a couple of interesting differences. Namely, what is the big difference? Like they have taxis?
They have taxi count, motorcycle count, bus count, and we have camera ID, car count, truck count, taxi count. So where we overlap is car, truck, and taxi.
Yeah.
MTA has motorcycle, bus, and we have camera ID.
And their definitions of those things are slightly different than ours because of what we can detect. But okay, so then you're getting to this slide you're talking about where there's some.
Yeah, so this was, so when you filter the DOT cameras for Manhattan, you get a bunch of these, which was not fun to manually sift through, but it worked. And here's an example of what one of our camera feeds look like. So this is on the Manhattan Bridge. This is one of the camera feeds. And this camera feed averaged 2 cars per hour on the Manhattan Bridge. Can anyone tell me why? The bridge is in the way, obviously.
Yeah, we just don't have, it's just blocked. And there are quite a few instances, we have some screenshots of stuff like this where obviously it's wrong and starts making you think like, what? Yeah. And it's not, sometimes they're just dirty cameras or black and white cameras.
Yeah, or sometimes it's raining. And go ahead, Steve.
Bridge also tilts when trains go over.
Yeah.
So you don't have a steady image.
Yeah, we don't have a steady camera image either. So that would mess up the YOLO algorithm if the camera is physically moving. Wind as well would affect that. Sometimes it's raining, although we do have an example of when it was working perfectly when it was raining. But yeah, visual data, especially with low camera resolution, not the greatest, especially when you're saying there's 2 cars per hour on the Manhattan Bridge.
And if you watch the feeds real time, then you as a human will totally be able to count pretty well with some of these cars, even though the visual data is so minimal. It's kind of an amazing difference. So let's look at some other examples of this.
So this is on Vanderbilt Avenue and East 45th. This camera was one of like the highest trafficked areas, so an average of 32 per hour. So that one is pretty much, the more accurate ones are going to get a clear view on the street like this. I'm also now realizing per hour counts overnight. So it'd be more interesting to see kind of like a rush hour number.
Well, we have some charts and we plotted
Sure,
graphs. That's true.
But yeah, this is a image of a camera that is not obstructed, way more likely to have more accurate data.
And a lot of this project, like over the last few months, was just Isaac and I getting together on Zoom every few weeks and looking at what we had and me just asking dumb questions. I was going in and be like, let's see what we can see and count. Like, do we have we have Tuesdays. I have the average Tuesday, which I thought was interesting for some reason over this 16-week period. But yeah, there's a lot. What else anything else you want to mention about this?
Yeah, I was just going to say these dots are basically the hotspots of where we saw cars. And so one of the reasons I singled out the Manhattan Bridge, because you could see these dots are a lot lighter, which made no sense until I actually looked at the camera feed and realized there's no way you're going to measure cars with a bridge in the way. So
Is a question you want to say something?
Just curious, looking at this photo,
yeah,
and can it pretty accurately filter out parked cars? And
Great question.
You have to compare like
We addressed
one
that.
image to another.
Let's move up and look at some of those examples. Yeah, there's tons of cases like that. That's just like sometimes it's like, oh, totally part of the street. Other times it did count them, and let's move forward and look. Oh, so this is so
this was at Koch
hotspot.
Bridge. Random question. I was like, where are the trucks coming in? And so the darker spots are truck hotspots. And this one is just one that clearly made sense coming right off the bridge. Yes, here's just 6th Ave and 34th. So this is the algorithm running in real time. A quick blip there, you saw the camera is being serviced. So that happens as well.
So this is when once I had a feeling for like what we sort of could do, then we start, from my point of view, trying to make like rules of like, okay, what are we going to detect for? What are we going to count as taxi? And so this is basically us looking and the machine sort of doing a basic count based just on the size at this point, right?
No, size and also just image recognition.
When you say image recognition, what are the criteria that are in there?
Whether or not the pre-trained YOLO recognized the car, truck, and the taxi is a special case.
So you're tweaking these knobs still for this?
No.
Not yet.
Yeah,
Okay.
so I'll get that.
So not yet.
But quick, interesting thing here is I'm not sure what this is, but it's kind of the pedestrian barrier. It's getting picked up as a car pretty frequently.
And sometimes at
And
pretty
only
high
this-
confidence. This number is the level of confidence,
Yeah,
right?
we have the confidence metric here. Sometimes it's a truck, sometimes it's a car, and it's neither. It's not a vehicle whatsoever. And that's an interesting little tidbit. And every minute or so, you see the blip come up that says this camera is being serviced. So sometimes the cameras go down.
Okay.
So these are the knobs I was talking about. So the YOLO algorithm, you only look once, has 2 levers that me as a developer can kind of toggle. It has more, but the easiest ones to play with are the confidence threshold and the IOU threshold, intersection over union. So confidence threshold is self-explanatory. If the model is
How
confident,
certain you are
Yeah.
that something is true or not.
I only care about
Just in case
things
it's
that
not
you're 40% certain is true. And so everything below 40%, I never even see, and we never even count it. Intersection over union is a little bit more detailed. So that one says, if I have 2 overlapping boxes, if they overlap by more than 60%, count them as one object. If it's less than 60%, count them as 2 separate objects. And so these, you could think of these, like if I was a pilot, these are 2 knobs I have in my cockpit that I could play with to tweak how well or bad the algorithm performs.
And as a UX or HCI person, I'm looking at some of these very, rough, like, intersection of union 60. The ability to recognize 2 distinct objects or the color of an object. How do we as humans help train these machines to do a better job of looking at things? So we had to, or do you want to go to the next slide?
Sure.
Like just start saying like, okay, what are we actually trying to do here? Is that a bus or is that a truck? Should we just, in the end, we decided to ignore buses because with the, limited sort of knobs and dials we had, there was pretty much half of, it was 50-50. So we're just sort of looking and saying like, wait, how can we teach this and help train? And then
Right.
Isaac had to go through and, make notes for each camera and each image saying, well, count this or don't count it, but is it offset by parked cars or other trucks and things?
Sure,
This
yeah.
is one of the big sort of rules that we were trying to teach the thing, like when not to count things, objects.
Yeah, and these are just 2 examples of what made buses so hard. I think the bottom one here, here's a bus getting classified as a car with 58% confidence.
Yeah.
And then up there, it completely ignored the bus. Whereas a truck got identified with 83% confidence, and I think pretty much everything else there was correctly labeled within the limited resolution as a truck in the back, and then another car behind the truck. So yeah, just some detail on the issue with buses. I guess another kind of large issue with buses is I don't have time to look through every single image to really like clean the data into a format that the algorithm would perform well on buses. And so even the determination that it wasn't working well with buses just comes from a limited amount of time flipping through images, not really taking detailed notes, but just realizing, most of these buses are wrong. I'm not going to count them.
So correct me if I'm wrong, Ajay.
Sure, yeah.
The way, like, a possible step forward for this kind of project would be to, publish a whole bunch of images like this, and then just crowdsource human beings to look and make notations, because that's essentially how we train the model, right? Is we actually centaur design, or whatever you want to call it, a companion, where you're working with the human actually is looking at an image and saying, oh, by the way, this is a bus parked, and just making observations, as it were, for the machine, so we can train the model.
Yeah, and that's how the original model was trained. So the original model was trained on something called the COCO dataset, COCO. Like I said before, it had 80 plus different classes. And yeah, it was crowdsourcedly labeled, and it's now available. The model is now available in open source for a developer like me to come in and just use it without much effort. But as Tim said, a way to fix this problem would for us to crowdsource images of the congestion zone, and for humans to hand label what a bus is, and then I go back, retrain it on the images that we labeled ourselves, and it'll perform much better on buses. Yeah, so to answer your question, we do count parked cars sometimes, but here is an example where vans are pretty much trucks in our data set for some reason. Vans were counted as trucks pretty much every time. And this is an example of a van parked being classified as a truck. And at least through anecdotally flipping through the images, this happened pretty often. And another thing is, not all the DOT cameras are color. Not sure why, but there were some feeds that were just black and white. This is way harder. It's technically an entirely different problem to solve from a technical perspective. And I didn't make any attempt to fix the algorithm to account for black and white feeds. So I kind of just left it. And so these cameras, I would imagine, are completely wrong, even though I didn't go through each individual one. So here's another one where a pickup truck is counted as a car. The MTA counts pickup trucks as cars too. So this one we're actually the same.
Now, this is really interesting, I think, in terms of like scaling or moving this kind of intelligence to another context, is like what the MTA calls pickups or cars. Like, what is a bigger car here in New York? It's a smaller car. Sorry. What is a smaller car here in New York is a bigger car in places like Europe and other cities. And so just having a definition of what is a car, how is it getting taxed, how much pollution is it creating? But it actually makes sense in a way what the MTA did here, at least as far as we can tell, because they are actually the size of a truck by any reasonable standard, but they're being used as private vehicles. So that's, I thought, kind of an interesting thing about the actual traffic that's coming in and out of this city. So I think that was a good choice. We'll talk to Matt afterwards, see if that's the reason why, but it was a good choice on the MTA's part, and ultimately ours as well. It's just a car for our purposes.
Right. So our parked cars in our count, they are sometimes. So here's another image where pretty much every parked car is ignored. And still don't understand the reason for why this happens and why it sometimes doesn't. It technically should count parked cars every single time. There's no reason why it shouldn't. It doesn't have an understanding of this is a moving car and this isn't.
I guess also, so it's not comparing like one image to the next to see.
No, it's not. It's each image.
No, it's pretty dumb. Yeah, it's not doing that.
Well, I also coded it that way for sake of.
But I'm also curious, just when this stuff comes up, that's when I'm like, okay, wait a second, what is it seeing? How is it working? Like, is it somehow the movement? Like, it thinks this is part of the pavement or whatever?
Yeah.
But anyway,
But
Yeah, I've worked with the Shkokovesa and the Yogolify, and I've noticed that it might be because the cars are not moving, that it's detecting the cars that are moving.
that are moving. Okay.
So maybe the moving aspect is probably what
Yeah.
gets captured instead of the park.
Possibly, yeah. Yeah, and it probably this parked car is from an angle that could be misinterpreted as a lane, so that could also count. Where these are very clearly off to the side by the sidewalk. So yeah, that could make sense. Yeah, I did. That's something I didn't investigate further. But in this image, besides the parked cars, it's actually performing pretty well. The truck classified with 87% confidence, car high 50s, and a couple other cars as well. So here's another fun one. The crosswalk sign gets classified as a car with 48% confidence.
It's not a car.
And here's just an example of a camera being down. So the camera is being down, and the camera is down. This one didn't say why. Sometimes it explicitly says down for maintenance. This was a feed that was just down. No idea why. Or no communication from the DOT on why. So here's the fun part. So through these images, you've probably seen yellow taxis.
It's orange.
Yellow, some hue of yellow. And
Why? This is so obviously a beautiful big taxi to me. Right?
true, but so the way I find taxis is that I first classify as a car, and then I ask, is the car yellow? And if the car is yellow, then I say it's a taxi.
Now, is your definition of car having anything to do with movement? Is that in that algorithm somehow?
No, technically no. Technically, each individual frame is just a frame.
But this bus is not always there, but this
That traffic light is always there. Yeah.
All right.
So let's let the yellow algorithm is pretty fun. But so yellow, we can't see license plates, so we can't technically count taxis. So I had to put a little hack where I define what the definition of yellow is, and I tell it for every car you found, does it fit this definition of yellow? If it does, then count it as a taxi. And you'll see how this affects our taxi count versus the MTA's taxi count pretty drastically.
And as a dumb designer, I got really excited. So I'm like, ooh, I know what that is. HSV, right?
Anyone know what HSV
Oh, does
is?
anyone know what it is? Stands for?
It's a separate, not too many color theorists, which is fine. So us humans, we see in RGB, and I had to
Red, green, blue.
red, green, blue.
Approximately.
That is our wavelengths of light that we perceive. Computers could see RGB as well, but they see HSV a lot
I
better.
don't see anything.
They can understand HSV a lot better, which stands for hue saturation value. So it's a different color palette that computers can use. And so part of what I had to do was translate the RGB image into HSV. And then from HSV, we can define a set of colors within HSV that is yellow. And I tell the computer if at least 15% of pixels in this car is yellow, label it as a taxi.
15?
15, yeah.
What's it? Oh, there it is.
15%. So the bar is pretty low. If 15% of pixels in this car is yellow, label it as a taxi. And you'll see there's an example here where that goes.
So obviously you've got ambient light. There's all different ways, but even just actually putting like a color meter on a point in space and saying, look, this is like a certain level of hue, a certain level of saturation, a certain value. You know, as a visual designer, it's an interesting thing to try to figure out, like, how do we measure and calibrate and actually define colors numerically in a way so we can talk with each other, designers and engineers, and make something that's truly useful. And it's definitely really hard.
Yeah.
Because even you could take a whole bunch of different ways of measuring and defining colors, and there's so many different color models out there. And this is just a really brute one, but a great starting point because, I mean, yeah, it kind of worked to roughly.
Yeah, it roughly worked. And you'll see when we get to the data, but here's an example where 15% of this car is technically yellow, but it's a school bus driving by. So when it did this bounding box and said, hey, this is a car, 15% of the pixels in this bounding box is yellow, label it as a taxi. And it was pretty confident, 86% confident. Not true whatsoever. It's just driving next to a yellow school bus. And so that's part of the nuances in the yellow algorithm.
And this is like really fun, maybe as like pulling out images or even just writing an app to detect all of those kind of situations and then feed those images to humans who would help, the machine learn and train the model better to distinguish between, well, this is union intersection, essentially, mixing up.
So yeah, that's a good comment. So the intersection over union value that I could control, it didn't classify this as a bus, which meant that it wasn't going to combine the two boxes as one, which left the algorithm to just classify this as a car. Then it asks how many of these pixels are yellow, more than 15%, goes to taxi at 80%, 86% confidence.
Was that the order, Isaac? Like, so first it was like, is this one or two objects? Oh, it's just one.
Yeah, so the intersection over union takes precedence over pretty much everything. And so for this one, these two boxes are allowed to intersect and they get classified as two.
Yeah.
These probably intersected, but not enough. It gets classified as just one.
And this phenomenon of visual cognition in humans, by the way, I don't know if this is interesting or boring, but like the Gestalt theory, the fact that we can recognize foreground and background and distinguish, pull out objects like that is just amazing.
Yeah. So yeah, that's a good point. So the computer cannot understand foreground or background. So that's part of what the IOU threshold allows you to do. It's kind of a toggle between how far are you? Because I have no idea. As a computer, it's just a two-dimensional image. Don't really process in 3D. So here's some examples of the yellow algorithm. So here it's pretty well taxi at 87% confidence, and that's completely right. So it's a yellow taxi. Over here, not so well. The car up front is clearly a taxi. It gets labeled as a car, but still did good on the two trucks in the image and the cars in the back.
What can you see? Is that 0.9? What's the
That is
on that?
0.3. I can't see.
I can't see.
Yeah, I don't want to guess. But yeah, it's
Sometimes it was interesting to see the confidence, at least I thought, the confidence level. Because it's like, okay, fair enough. But anyway. Still, but this is just not moving. That's
just not.
And that's YOLO? Like that's...
Well, traffic lights aren't in the COCO data set. So
it's Coco, sorry.
Yeah. I'm not surprised it didn't pick that up because traffic lights aren't in there. So it would...
It just doesn't recognize.
It doesn't know what a traffic light is.
Right.
So if a traffic light ever gets picked up, it's going to be misclassified. It's going to be because it got misclassified as another vehicle.
And this is still blowing my mind, like a little bit, like over the last few years working with some of these, I don't know if we even want to say LLM or AI, whatever the hell it is, but like you've got this corpus, right? You've got all this data that you train a model on. And so like it really is just, for me, plus ça change. Like nothing's really changed. Like you've got a set of inputs. Like you don't know what something is. You just don't know what it is. The computer, I mean, the machine.
Yeah. But here's an example where it worked perfectly. So it's raining, bad resolution, even worse resolution, and it got every single taxi. This taxi here, 85%. This one, 50 something. That taxi over there, oh, that got labeled as a car. But these two taxis here with raindrops on the camera still got labeled as taxis. So it's also not bad, and it could also work in the rain. Another thing on the yellow algorithm, I couldn't find an example here, but I did see it. I just didn't record it. Sometimes when a white car is driving in the early AM with the street lights still on, the hue from the street light onto the yellow car makes it a taxi with a very high confidence, which was fun to look at. But I didn't remember to get a screenshot of that, but that's another nuance in the yellow algorithm that I saw. So the MTA has great data. It's publicly available, being talked about in 301 right now. We compare our transit techies counts with the official congestion pricing data. And I realize we have 15 minutes left.
Let's open it up to questions. I mean, if you want to flip through,
I'll flip through the graph.
We've got a bunch of these. We can make these available to all of you. Just trying to compare our count with the MTA official count. So trying to make some sense of some of our count as well as theirs. But I think hopefully, we can make, I guess, the code available.
Yeah.
It's really not that hard to do yourselves. And we'd love to see how might we take this forward in some way and make it genuinely useful.
We have some graphs. So we undercount cars. We undercount pretty much everything. These are cars on weekdays, weekends. This is a taxi count, so we do not even register anywhere near the amount of taxis they actually are. Because remember, they're looking at black cars, the license plates, where we have a janky yellow algorithm that I wrote in half an hour. So
But
yeah,
on the original purpose of this, because how confident are we that this is? Oh no, this is theirs.
yeah, the blue one is
So if
there.
we go to the next one, like how confident are we in our sort of car count
In our car count,
and what we call as cars? Because we took out trucks, we took out buses, we tried
Yeah.
to take out taxis, which we did.
I mean, the seasonality is correct. So
Yeah.
we get the ebbs and flow of the city, just like the city, just like the MTA does. But we just undercount for all these various reasons. I'm surprised we didn't overcount actually, because as a car drives through the congestion zone, technically I should be counting it multiple times. That didn't appear. So didn't investigate that, but it could be either a limitation in YOLO or some type of like hardware issue. So I ran this on my GPU. I'm not a GPU programmer, so I didn't optimize the running of YOLO to make it, I guess, kind of computer vision friendly. So that could be another reason. But we undercounted, and that was a shock to me. I thought we were going to overcount because we would count the car driving through Manhattan.
So just in case people don't know, like
Sure.
we're comparing the CPU with GPU, which is like a central processing unit versus
A graphical
graphics
processing unit. Yeah. So a graphical
The hardware
processing
is
units,
quite tuned to the graphical kind of information.
yeah. What you could do with graphical processing units is you could have the algorithm running on multiple cameras at the same time versus a CPU sequential. If you have to run the algorithm on one camera kind of like in a line versus in a parallel way, you could run it on all 225 at the same time. I did not do that optimization of running the algorithm on every camera all the time. I did it one at a time despite having a GPU. So that's the technical nuance there. Happy to go into details if you're interested. But I think with time,
Yeah, let's just
It's
open
a
it up
Q&A,
and have
yeah.
a chat. We're
Charlie.
over the
Great talk.
Yeah.
And I look at this one, and sure, has sit around. I'm guessing it might be February 8th. This one is snow because we have our data is that we have some weirdness of February 8th. And I'm wondering if that's because if that is February 8th, and if it is snow related,
It looks like it could be.
because there were less cars on the road, or does that have an impact on YOLO's ability to?
when there's snow covering the cars, for
was there any
example.
white
yeah, that would
on
that
static cars? Does it kind of dip the ability to count, or maybe the less cars out?
I'm not sure on YOLO's ability to do that. It would absolutely affect taxis. Or our version of taxi.
We did actually use the YOLO to do this, and with snow we had less accuracy.
Yeah.
It definitely impacted our count.
Interesting. Okay.
Yeah, I did the similar thing, but with street lights. So I had to do a custom like pre-modeling. I noticed that there's a YOLO V8.
Yeah.
I know that's in beta, but have you tried working with YOLO V8 at all? Or
Not yet, but
No.
that would be a great idea. We could,
Yeah.
Yeah, the more updated model. No, we haven't.
yeah, and then to make your data more accurate, would it instead of using a pre-trained COCO data set, would you use like a more custom data set but then that would take longer and
Yeah, we'd have to put a significant amount of effort into labeling the data set. So I think part of the issue is I'm not sure where the traffic data within the COCO data set came from, but New York City is just extremely unique. So yeah, our buses are unique. They're super large compared to, I guess, the rest of the world, wherever COCO got their bus images. Our definition of truck is also different. So a truck here is like the biggest truck ever. A pickup truck here is a regular truck overseas. So it's different. So to really, really get this more accurate, it would have to be manually labeling data and then feeding into, I guess, YOLO V8, the most accurate version of YOLO today.
I think there's an opportunity for that, especially with the New York City visual data. That's really, I think, the provocation. Yeah, go ahead.
Yeah, I was gonna ask, do you know like what types of photos are in the COCO data set? Like, is it traffic cameras? Is it Google images? Like, what types of photos are
It
there?
was let's scrape the entire internet. So
Okay.
all of the above. Yeah.
Okay.
So were you guys able to compare before and after congestion pricing? You have a
Not
little data sets before, I guess.
Yeah, not really. So this graph here, we have some data from the 26th of December. It pretty much follows the same line, but I mean, this one's kind of lower, but it's during the holidays. Really hard to tell.
Yeah.
Cool.
Unfortunately, no, that was like we turned the machine off by accident and we didn't get started in time. So the original idea was to do like a real nice sort of before and after. But
But yeah, I was originally running it on my laptop, and then I made the egregious mistake of closing it one day, and then the algorithm stopped running. So that's why I moved it to my other computer. But you see the MTA obviously 0 during this time because it wasn't.
But now we've basically got these 16 weeks or so. And so it would be nice. I'm not sure when we could hit a midpoint and then start measuring for another 4 months after to try to do some kind of before and after, like that's what we want to see, right? Less cars come into the zone, hopefully. Yeah.
Are you going to be looking at changes in truck traffic at time of day?
Yes, I have an interesting graph.
Yep.
So we actually overcount trucks on the weekends. So this is one of the rare instances where our count was higher than the official MTA count. And that's pretty much because trucks and vans are parked on the street during the weekend. They're not actually going through the zone. So this was one of the rare instances where our count was higher.
And again, we don't have access to these cameras. So I would love to know from MTA, like, can they make some of those open? Like, yeah, what's the difference? Because it could be,
I mean, here, like 9 minutes. Oh.
I'm interested in the sample rate of your camera features. So you're saying that you sample every minute?
Yeah, I sample every minute, but I aggregated the data per hour. So, because I was just running out of space on my laptop, so I
That's
just.
the reason of the undercounting?
Well, no, because the MTA does it every 10 minutes, but then I also aggregate their data per hour to get the apples to apples.
Sorry, we talked about parked cars. So are you saying that you're just trusting the algorithm to pick up parked cars as parked cars and then moving cars up as moving cars? Just wanted to clarify, like you didn't do anything else, right? To further distinguish.
No, I didn't do anything else to further distinguish because that would require kind of like hand labeling. So I guess these two slides tell the story of we actually have no control over whether or not parked cars get picked up. Here, the assumption is kind of from this comment earlier that it's close to the sidewalk, therefore it's parked, that YOLO somehow understood that. And then in this image, that parking area could be misinterpreted as a lane from this angle specifically, but we made no distinction. So
as we go through, yeah, we can't really distinguish, but we were looking and we noticed that sometimes they're counted, sometimes they're not. And that's something else, we could work on a little bit.
So for this image in particular, you didn't happen to just stare at it and see if the white car folds at all.
No, these are.
Well, yeah, I mean, when I took the screenshot.
No, these are parked, right?
Yeah, those are parked.
So we did watch the feed and be like, oh, those are parked cars, but it's counting them. This is bad machine, bad.
Oh, I see, okay.
Bad robot.
Yeah. So, yeah.
But we're like, oh, it's good robot. You tried. Good robot. You tried.
Any question?
I just wanted a quick one. Where you said that there were certain cases where there were like features in an image that were getting incorrectly flagged.
Mm-hmm.
Are you able to make any modification to say like ignore this part of the image in this camera, or does that become too complex like within no rules?
Technically, yes, but it'd be a lot of
Feasibly,
labor.
right?
Yeah, it'd just be a lot of labor to do it. I would especially want to have done that on the bridges because the bridges are more or less static, and I could say ignore this half. And but yeah, it's just a lot of manual labor to do that. Technically possible though. How about a new person?
Sure. I was curious. You mentioned that you don't have license plate level resolution. Do these cameras in general have that kind of resolution?
No.
The traffic cameras?
So the DOT don't, but we think the MTI does.
The MTA does
right.
share,
Yeah,
but those cameras aren't public. The DOT does not.
Yep.
Are you?
So if I think I'm remembering right, your system here doesn't have any concept of like entering or exiting the zone, right? It's just counting cars going through.
Yeah.
And then so then getting that total is just sort of a naive sum of all the cars seen by all of these cameras? Or-
Yep.
Okay.
Yep. By the 225 that I handpicked. These.
I would say this is sort of a proof of concept in a lot of ways,
Yeah.
Yeah. And so we could fine tune it. And there's different ways to, pardon my terminology, but like bring it to market or launch in some way to take it to like a beta or a next version. And yep, hopefully we can. Maybe, who knows? Is there another question?
My question is more so of like how you're running it. You said you keep it on overnight.
Yeah.
And then, like, what's the main challenge, like, other than distinguishing taxes being yellow? Like, what was, like, that was the main challenge? Or?
So I would say, what's the main challenge? I would say actually one of the biggest challenges is trying to get the right IOU threshold, because during times with less traffic, it picks up a lot of it misclassifies a lot of things as cars, but during rush hour, you kind of want that. You kind of want cars that are close together to be counted as two separate objects. And so trying to figure out what's the right IOU threshold to calibrate for both times was the biggest technical, at least annoyance to me. Did that answer your question?
Yeah.
Yeah.
And I would try to take, intersection object union and sort of double click into it and try to make a little bit more of an intelligence around that somehow to have a few more knobs and dials for that particular area, maybe.
I think one thing I could have easily did was change the threshold based on the time. That's something I could have easily did, Oh, sorry. Here and then Steve. Go ahead.
Oh, you correct.
Oh, yeah, go ahead.
I just want to make sure I understood. How many times have you taken for single location? How many times have you taken a snapshot?
Once a minute.
Okay, but the image is being updated about once every 2 seconds.
Oh, okay.
On the,
Yeah, we're only doing
okay.
the real time data. There's a lot more data.
Yeah,
we could
Understood. I was just asking.
Yeah.
once
I'm
every
just
60
constrained
seconds.
by like physical hardware space. So yeah.
Okay, and you're doing this, your local machine and so
Yeah.
forth. Okay.
Yeah, I was just gonna say, I think it's really cool you guys did. I'm a reporter at Bloomberg, and we published a story that was very similar.
Nice.
But we set up a camera and counted cars going in a congestion zone.
Yeah.
But we looked at doing the DOT cameras first, but we basically decided
Res
there were
same
stuff. It would be too low res and like all this other stuff. So like, since we were interested in publishable results, we couldn't use those, and we ended up just looking at basically one intersection for the whole month.
Yeah.
But yeah, if you had been able to have more resolution, you just would have hit a lot more technical challenges that would have made it really difficult. It required a ton of resources to do.
Yeah.
So
There's a lot to be said for taking the low res and just having really simple, like really thinking about the very few simple rules we can train the machine to do. And that's the invitation and provocation now, honestly, is like you could, like, if every, third house had a little machine in their basement just looking at 1 or 2 cameras and taking maybe some pictures every 30 seconds or every 10 seconds over a certain period of time and then analyzing it, we could all together make sense of this and, check on other sources of data and make some useful calculations, for sure. But that's really cool that, that's you could do
That's a
this one.
confirmation of kind of what we did.
yeah.
Did you come up with a number you had good confidence in?
So we weren't confident in counting the number of cars, but instead we were looking at the share of different types of cars that were on the road.
Okay.
We were more interested in people were saying this was going to stop, certain types of people from driving into the city and that kind of thing. So we were more looking at the percentage of private cars versus taxis versus trucks versus vans.
Oh, that's awesome. I think this is a successful proof of concept in the sense that, yes, we can actually count. And if you set the rules specifically and rigorously enough, then you can actually get really useful numbers, but usually quite focused or.
Yeah, I will say algorithmically, there's lots of work to do. I could have made the algorithm much better, but just time constraints. All right, last question. I know we have 1 minute left.
Yeah, I don't know about image recognition coding, but I was wondering in the case for parked cars, is there a way you could just say, if the object hasn't moved in 2 hours on the timestamp, could you make that just disregard the object?
Yeah, that's something we do.
Oh, okay.
Yeah, but I didn't, like I said, there's a lot of room for improvement. I didn't let the frames talk to each other in a sense. So each frame wasn't aware of the one that came before it. But if I were to implement that, that's an easy thing to do to take out the parked cars.
Yeah,
So-
some days then.
Yeah. So we've got 1 more minute. Any last question there? Go for it.
Yeah, I was just wondering, say you change the camera source and it was a top-down satellite image, would your algorithm be able to parse out the cars, or would you have to retrain the model?
Yeah, I think not YOLO. not the Coco data set, but another data set has satellite imagery of vehicles too. Yeah.
Go ahead.
There's also like LiDAR data set.
Yeah.
Yeah.
It's much in a kind of different direction. Is that something that you think could be implemented later, or?
Maybe could, but to get a LiDAR scan of like an open space,
Yeah,
like
that is a more complex.
that's really hard. Yeah.
Yeah.
I have seen where you have like an aerial, like a drone or a helicopter, get LiDAR of the street, and then you use that. But at that point, with all the effort you did to get LiDAR images, you could have used satellite. So, but yeah.
It's labeled there. So that's it. We're
Yeah, time is up. But yeah. Thank you all for trying.
Thank you for keeping this, Tom, over.